15.86 kilojoules of, that's how much work that the gas is doing. Heat into the gas total, okay. Well, you could just look at your picture if it's complete. Heat into the gas, I'm putting in 34. I'm also putting in 27.96, right? So 34.53 plus 27.96 minus how much am I dumping? 46.6, right? That's why it's good to have these colored arrows, stuff you can draw it nicely, 46.6. So that's how much I'm putting in, this much heat, and then the gas is dumping that much heat to the surrounding. $15.89 kilojoules. Well, it's pretty close to the work total. Okay, well then what's the delta E of the gas? During the first stage, it's isothermal, so the energy doesn't change. But in the second state, the energy drops because it cools. So what was the energy drop? Negative 27. It was isobaric, right? So let's see, negative 27.94. Okay, and then what was the change in energy in the isovolumic? 27.96. Actually, it's a rounding error. If you did it right, what should happen? This one should also be 27.94. This one should be 27.94. And what should the change in energy be? Because it's coming back to the same state that it began. Same temperature, same pressure, right? So this should be 0 if you did it right. Oh, okay, that's a sign that we've done it right. So during the isothermal, change in energy is 0. Isobaric, change in energy is negative, then positive, but they're equal and opposite. You see? So if I did it right, these two should also be the same. That means all the work that the gas is doing is by virtue of all the heat into the gas and out of the gas. So this should also be 15.86. Is there another question we can ask? Yeah, questions are endless. What's the heat efficiency of this engine? What is the heat efficiency of the engine? So if we made a whole engine out of this, how do we calculate its efficiency? What we do is we calculate the total work done by the gas, the total work done, including its negative, the work total, divided by how much heat went into the gas. And that's how efficient that engine is. In other words, how much heat do I have to put into you, and how much work can you do? And the same thing you can do for the efficiency of your car. You're getting energy from the gasoline that you're taking, you're burning that. That's the heat into the engine. Then how much work are you doing? You calculate the number of miles that you can drive. Let's say you fill up 20 liters of gas. You calculate how much chemical energy is in 20 liters of gas, right? That's the heat into the gas. Then how many miles can you drive on that? That's the work done by the car, by the engine. And then that gives you the efficiency of the car. So typical efficiency of a car is about 15 to 20%, maybe 25. Electric cars, 40%, maybe. So let's see what our efficiency is. What's the total work done? 15.86. What's the total heat into the gas? Well, you say 15.86. So 100% efficient engine? No, 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 no. You don't count the amount that you dumped. Only what you did to put in. So this is the engine. This is what you dumped in the form of heat through the muffler, right? You don't count that. You count only what you're putting in, which is these two. So in this process, it would be this and this. So if you add those two, what do you get? 3, 6, 9, 5, 9, 14, 1, 5, 7, 12, 1, 4, 2, 62. It's not that efficient. Then multiply it by 100 to change the percentage. So 15 over 62, that's gonna be about 25%. It's not bad, it's better than a car. Hybrids are probably kind of higher. What does that come out?
Yeah.
Let's see here. It is a simple list. Don't give me paragraphs. You know, we want everything very, very fast and modern, right? We don't have patience for long paragraphs. Give us quick, quick, quick. 40%? No, that doesn't make sense. That's improvements. Give me a list. Give me a freaking list. The modern gasoline engines have a maximum thermal efficiency of about 20% to 35%. Okay, 20% to 35% when used to power a car. At high speeds, efficiency in both types of engine is reduced by pumping and mechanical friction losses. So if you're driving at 60 versus 80, your efficiency goes down at 80. So you might get somewhere quicker, but actually it's less efficient. Huh? It's interesting. So that's actually a pretty good range. So 35% is probably for hybrids. 30 to 35% is for hybrids. And then the regular cars are like 20%. Let's see what's the electric cars. Of course, for electric cars, the input of energy is in the form of what? You're not burning coal or something or gasoline, it's electric. According to U.S. Department of Energy Office of Energy Efficiency, electric vehicles convert about 59% of the electrical energy from the grid to power at the wheels. That's a lot, wait. 59% efficient? Conventional gasoline vehicles only convert about 17 to 21%. That's crazy. So would you say they are 60% efficient? Wow, well, if we just take that at face value, I thought it would be more like 40. That's crazy. So it's taking its 60% of its electrical energy, converting it to the energy of the wheels. Whereas the regular car 17 to 21, maybe hybrids are like the 30 to 35. See? So for our engine, what was it? 25%? Okay, so that engine is like it's like a regular car, not hybrid, but it's not an SUV, right? SUV would be more on the closer to the 17%. Okay, so on Wednesday we'll do adiabatic expansion. We finished the isothermal today, okay?